So this is number 27 for the Chapter 7 homework set. A 40-kilogram child takes a ride on a Ferris wheel that rotates 4 times each minute and has a diameter of 18 meters. Part A, what is the centripetal acceleration of the child? Part B, what force does the seat exert on the child at the lowest point of the ride? And Part C, what force does the seat exert on the child at the highest point of the ride? Then we have Part D, what force does the seat exert on the child when the child is halfway between the top and the bottom? So here's my lovely drawing of a Ferris wheel. Since the diameter is 18 meters, we just cut that in half for the radius, so it's 9 meters across here. And the child is revolving around the Ferris wheel. We know that the Ferris wheel is revolving at 4 revolutions per minute, or 4 rotations per minute. And so Part A asks us to find the centripetal acceleration. We can use W squared times R here, but the only trick is that we have to convert revolutions per minute to radians per second. So we did this here, revolutions, minutes to minutes. Multiply that by the radius, which is 9 meters, and you get 1.58 meters per second squared. Part B here asks what force the seat exerts on the child at the lowest point of the ride. So I just drew the bottom part of the curve and the seat here and the child. And this is, I guess, like my free body diagram, and I would say that the normal force is going up, opposing the weight of the child going down, and I drew that up is positive because the acceleration is going towards the center of the circle, and in that case, center of the circle is above the child. When you sum all the forces in the y direction, it is n minus mg, so n is positive up, minus mg negative going down, and that F equals ma, so that's force equals mass times the centripetal acceleration. We just work this for the normal force, and we move mg over, factor out the m, plug in your values, and you'll get 455.2 newtons. We're solving for the normal force because the normal force is the force that is being exerted upwards toward the child that is keeping it on the ride. Part C is quite similar to this. It's just the reverse of the circle, so the child's at the top. But in this case, down is positive because the center of the circle is below the child. So when we sum all the forces, it's mg positive minus n equals the mass times the centripetal acceleration. We just reorder our equation for n once again, factor out the m, plug in your values, and you'll get 328.8 newtons. And then finally, part D here is when the child is at the side of the Ferris wheel. I drew this in a wonderful way too. Here's the seat, here's a child, and in this case, inwards is positive because the acceleration is going this way. In order to hold the child onto the ride, the center of the circle is to the left, and so I drew that arrow to designate that. The sum of all the forces is the sum of the forces in the y direction, because the forces are going in the y direction, except F equals ma, and we know that the centripetal acceleration is only in the x direction, so there's no centripetal acceleration in the y direction, therefore this is 0. So then n minus mg, n equals mg if this is 0. We plug in our values to find n, and it's 392 newtons. Another important thing is that at the bottom of the ride, the normal force is the greatest because it needs to hold the child up and connected to the ride. At the top, it is the lowest because the weight of the child is significantly contributing to the fact that it is still on the ride, and at the side it is in between these two values as it transitions from bottom to top.